Okay, perfect. Good morning, everyone. Thank you, first of all, to the organisers for allowing me to speak here. Now, today I'm going to be talking about two things. I'm going to be talking about classical path integrals and classical influence functionals, and how you can kind of derive these things from Koopman-von Neumann dynamics. Now, the idea behind these is kind of entirely analogous to their quantum mechanical equivalents, insofar as, you have a quantum path integral formalism. And from that, you also have this idea of an influence functional. And the purpose of these things is really to kind of be able to make a direct mapping, right, from a kind of microscopic model with a Hamiltonian evolution, where you've got a system and environment. And the classical influence functional allows you to kind of trace out that environment in a kind of consistent way. So you can directly map from your microscopic model to these kind of irreversible open system descriptions that you kind of see around the bottom here. I'm going to turn on my laser pointer for this. Now, what this means is that the ultimate results that we're going to see here kind of won't be new, right? There'll be things like Langevin equations and potentially Fokker-Planck equations. This is one of those rare cases where the Bible says something true. However, I'm hoping that there will be kind of something of interest to being able to see this technique and potentially being able to see some of the things it could be used for in the future. So to motivate this, let me first talk about an equation that we can kind of derive exactly using the quantum influence functional. This is known as the stochastic von Neumann equation. Now, it has a lot of interesting properties, and there's a kind of extremely non-exhaustive list of kind of papers that use this here at the top. But the thing I want to focus on here is a couple of weird things about it that make its classical limit kind of slightly non-trivial. So first of all, the thing to notice is that this is an equation which is stochastic in its nature. You have two noises in it, eta and nu. And it's to describe the density matrix of an open system interacting with some kind of environment. And it can be derived exactly using influence functionals. Now, the point about this is that you only get the real density matrix, if you like, after averaging over these noises. Now, given kind of we're concerned with Koopman-von Neumann dynamics here, one of the things you could ask is, okay, what is the classical limit of this system? And it's not quite as straightforward as one would expect, because while you can kind of take this equation of motion and look at the propagators, and you can see find the path integral and kind of say, okay, what's the action of this? That should give me an equation of motion. Why is that part of the quantum dynamics missing? And the answer obviously is, if this really was the right answer, this would be a very short talk. So there is something missing from this kind of heuristic classical limit. And what I want to show is that starting from Koopman-von Neumann dynamics, we can actually kind of find the right classical limit for this method by essentially importing all of the quantum techniques that we use to derive the stochastic von Neumann equation. So first of all, we have to start from Koopman-von Neumann dynamics. And I think all of the talks yesterday, and Dennis in particular, was able to kind of give a very quick setup for, what the difference is between Koopman-von Neumann and quantum mechanics. That your position and momentum don't commute. So you need to kind of invoke these two non-observable operators. I'm calling them lambda and theta. And you have this commutation relation between all of them. And so ultimately you can kind of write a propagator with this kind of generator for time translations. Now, once I've got this propagator, one thing I can do is, just like in quantum mechanics, I can actually make a path integral out of it.
May I ask something?
Oh yeah, sure.
Is the propagator the usual Koopman operator that is everywhere in the literature?
Yeah, it's exactly the one that you've seen before. If you put this in the phase space representation, you get the wave function and the density matrix is evolved by the Poisson bracket.
Thank you.
So once you've got this propagator, just like in quantum mechanics, you can have the idea of what happens if I just start to kind of break up my evolution by kind of taking resolutions of unity after infinitesimal evolutions at each point. And doing this proceeds almost entirely the same as doing it quantum mechanically, with the slight wrinkle that because you've got these extra hidden variables, rather than just kind of x and p bases, you've got these kind of 4 bases. And so you need to kind of derive what the overlap should be between these things. And this is kind of relatively easy to do. You do it again exactly as you would in quantum mechanics. So when you do this, the idea is that you kind of take your propagator that's kind of taking you from an initial point in phase space to a final point in phase space, and you represent it with a set of kind of, pardon me, you represent it with a set of infinitesimal evolutions. And this overlap, if you actually end up, or this expectation, if you end up evaluating it using the overlaps, you get something where you can start to see there's going to be these kind of delta functions, or these will turn out to be delta functions, I should say. And what they're actually enforcing is that you see this lambda variable looks like a kind of delta function enforcing one of Hamilton's equations, and then the theta variable is actually doing the same thing. So to skip kind of trying to kind of put it in the right form, what you end up with when you kind of do this calculation, and then you find that you can kind of integrate out the lambda and the momentum variables, is something that should not be surprising to anyone. And this is something that says, look, your classical propagator for a classical system actually turns out to be a delta functional enforcing the classical equation of motion. So this is probably, at this level, the most elaborate demonstration of Newton's second law you can imagine. It seems like classical path integrals are useless. They tell you nothing you don't know, right? It's a sum over all paths, but the only path that contributes is the classical path. So why would this be at all interesting or useful? Well, this is where the classical influence functional comes in. You see, rather than just kind of consider a single kind of system evolving unitarily, let's consider a joint system with an environment and an open system, right? So you have a kind of, your open system is described by one Hamiltonian, your environment is described by another Hamiltonian, and there's some interaction between them. And I'll say now, like, I'll express the initial condition on this system in terms of a density, but you could equally well do it in terms of a classical wave function. Now, the idea is, if you don't want to kind of reference this environment in your description of your dynamics, you kind of have two choices, right? You can either think about evolving the full system up to the time you want and then tracing out the environment, or like, is there a way of kind of tracing out the environment and having an effective propagation for just your open system? And the influence functional is one way of kind of achieving this effective propagation. It's done in quantum mechanics quite a lot. It's how you derive the stochastic Liouville equation we saw at the first slide, and it's also something that you can do classically. So what happens actually if you do this? So the idea here is, let's apply that classical propagator I showed you in the last slide to this joint system and then trace over the environment coordinate. And what you get no longer looks quite so trivial. So it's pretty unpleasant to look at, but this thing here is what you call the influence functional. And it is the kind of the trace over your environmental coordinates, so that this object now only depends on your open system coordinates. That is, you have a kind of a path integral that describes the evolution of the open system interacting with the environment that makes no reference to the environment itself. It is ugly, right? But at least it is kind of well defined. And once you have an influence functional like this, there's actually a couple of useful properties that immediately fall out of it. First of all, given that we saw that, okay, you know, your classical equation of motion, when you create a classical path integral, it should look like a kind of delta function on your classical equation of motion. So that immediately tells us that when we calculate an influence functional, we need it to, again, be of this kind of delta functional form if we want to create an effective equation of motion for an open system. The other part of this is that your classical influence functional, you can kind of explicitly see the dependence of it on when you choose to trace out your environment. Because of this, when you look at the kind of the form of the effective propagator and kind of take account of the influence functional, you immediately see that kind of that you're breaking reversibility apart from around a single special point. That is, that if you wanted the inverse of a propagation from T0 to T1, having kind of traced out the environment at T0, that's not just going to be the conjugate of this. You actually, the inverse actually has to be the kind of the conjugate evolution if you were taking the trace of the environment at T1. So you can kind of see on the right here that as soon as you kind of invoke an influence functional, fundamentally you're already seeing the irreversibility properties of the kind of open systems reduced evolution. Okay, so this is the kind of, this is the essential idea that we've got a classical path integral and we've got a classical influence functional. Now, what can we actually do with this? So I'm going to kind of take the rest of this time to kind of take you through an example of an influence functional calculation and how this relates to this stochastic Langevin-von Neumann equation that we saw at the start. So in order to kind of actually evaluate an influence functional, we need to have some kind of environmental model. And generally we kind of take something like the Caldera-Leggett model. There are other ones you can use, but I think this is the most transparent, and to a good first approximation, the whole universe is made up of harmonic oscillators. So it's nice to see, you know, a harmonic bar with a kind of bilinear coupling to your open system. So you take that model and again, your initial state, you can take a number of choices, but here I'm going to assume that my environment is initially in a Gibbs state. So what happens if I actually take this model? Well, first of all, this is the influence functional again. Lots of kind of terms that are pretty unpleasant, but what you find is that when you start to kind of evaluate this, you find that the delta functional, this delta functional again, conditioning your influence functional on another classical equation of motion. So this actually makes the functional part of the integration relatively easy, right? That this is a classical equation of motion. It has a kind of solution that you can write down. And so all you have to do here, because of this delta functional, you remove the functional integration and just replace this x here with the classical equation of motion. And at that point, in principle, this thing is completely solvable because it's just turns out to be a set of Gaussian integrals. In fact, you know, it's so easy, my dog can do it. Although I will admit they are an expert in the Barquette formalism, which that was dreadful. So when we actually evaluate this influence functional, we find that it has this kind of form, that it is it's kind of got this exponential form, which is what we would expect, and that it also has two terms. One that kind of depends on both theta q and q, and one that is quadratic in theta q. One final step I want to take before kind of talking any further about this is how we can kind of take a continuum limit on this set of oscillators. So you have this kernel on this theta q term as well, which depends on the kind of the spectrum of your oscillators frequencies. So when we take the continuum limit of this, we just kind of replace these this set of couplings with an integration over a spectral density, and we get this. And this is just to kind of bring it into the same form as the stochastic Langevin equation I showed at the beginning, which has a spectral density. So now that we've got this, what can we do with it? Well, like I said before about the properties of influence functionals, this has a slight problem. That in order to kind of derive an effective equation of motion, I need the influence functional to be of this form. Now, the first term here, this seems fine, okay? It's a functional depending on theta q, and then some other functional depending on your phase space variables. Whereas this term is actually quadratic in theta q. So that suggests that I can't actually take the path integral for my open system and present an effective equation of motion for it. So there's a couple of ways around this problem, but I think the most direct is to use something called a Hubbard Stratovich transformation. Now this is a really kind of marvelous transformation because it will kind of take some kind of deterministic Hamiltonian, sorry, not Hamiltonian, some kind of deterministic evolution with some known local parts to its evolution and map that precisely to a kind of time local evolution where you have a stochastic term. So that on average, this evolution is kind of completely equivalent to this one. How does this work? Well, if we think about this just in the simplest terms of you have some kind of quadratic exponential and you Fourier transform it, there are two ways of thinking about that Fourier transform. One is actually kind of having performed the Fourier transform, so you've got something that's still quadratic, but the other is as an average over a distribution. So on the one hand, you have something that's quadratic and kind of deterministic, and on the other hand, you have something that is kind of only linear in some variable, but requires averaging over realization. And you can kind of see this idea on the right-hand side. that with a Hubbard-Stratovich transformation, you can think about an evolution of a distribution in terms of taking a lot of trajectories of stochastic evolutions and simply averaging over them. Okay, so what happens if we actually do this? Well, we take the problem term in the classical influence functional and we perform the Hubbard-Stratovich transformation, okay? So that means that we actually go from this kind of quadratic form for theta q to a linear form, which is precisely what we wanted, right? When we do this, the Hubbard-Stratovich transformation by definition requires that your noise obeys certain properties. And if your noise obeys these properties, then this equality should hold. Now, if we do this, what we actually find is that we can put this back in and we can find an effective equation of motion because our propagator for our open system, when we put this back in with the influence functional, turns out now to just be a delta functional, which gives us our equation of motion. So what we've ended up with here is that we started from this, talking about this kind of quantum equation of motion, which is the stochastic Koopman-von Neumann equation, and asked, okay, what's the classical limit? And if we did it heuristically, what we found was that we ended up with a Langevin equation, but that this kind of new noise had disappeared completely. Whereas if we start from Koopman-von Neumann and implement the path integral and the influence function, we find that we actually get back this extra friction kernel. And so this is an example of kind of where you know, a classical limit is not totally trivial to begin with. But if we start with a Koopman-von Neumann formulation instead and just repeat the same steps that we did for the quantum version, we actually get a kind of unambiguous answer. Now, one thing that you might wonder about is, okay, in that heuristic classical limit, what actually happened? And the answer is that the Hubbard-Stratovich transformation isn't actually unique. That before I was just taking the Hubbard-Stratovich transformation over this term, but I can do this Hubbard-Stratovich transformation over both terms in my influence functional. And if I do that, I actually end up with two noises. So I can, rather than express this as kind of two terms, one of which is deterministic and one of which is stochastic, I can express it in a way that both terms are stochastic. And if I do this, what I find is that the eta noises correlations are exactly the same, and those correlations are the ones I found in the classical limit originally when I took from the stochastic Liouville equation. Whereas this extra new noise now, what we see is its correlations, it's not correlated to itself, just like in the quantum case, but now this kind of classical new noise, it has almost the same correlation function as the original quantum version, but this factor of h bar is now missing. So what I found now by kind of taking this alternative Hubbard-Stratovich transformation is something quite different to the quantum case, that when I took that heuristic limit, this thing disappeared. And the way of understanding this is that, okay, I've now got my two noises, but if you look at this kind of second term, this still isn't the form of an effective equation of motion. But when I actually look at what the propagator of corresponding to this classical influence functional actually is, okay, I've got a path integral where kind of I've got a delta functional that describes a Langevin equation without friction this time, just like I saw in the heuristic classical limit. But in order to express it like this, I have to kind of weight the measure, that each path has some kind of phase factor that depends on this random noise. So this, in some sense, is kind of telling us that when we took this heuristic classical limit, yes, the new noise dropped out of the equation of motion, but the part that we couldn't see was that the proper way of kind of taking the average of this now has to involve that weighting. So I think I've kind of, I think I've rushed through this a little bit because I was taking too long in my practice. So I've now overcorrected. But I'll spend the last few minutes kind of talking about perhaps some of the potential uses of classical influence functionals. So as we saw, you know, it's relatively easy to construct a classical path integral. This is kind of an example of a classical path integral of, you know, someone's life. once you've got a classical path integral, you can import the influence functional formalism, which is something that allows one to kind of exactly trace out the influence of an environment on an open system and express that in some way, either kind of as a path integral, or with the Hubbard-Stratovich transformation, you can get out a stochastic equation of motion. Now, using this, you can actually use it to kind of understand a little bit better the classical limit of some open quantum systems. But then also it raises the point that, as we've seen yesterday, there are a lot of discussions of kind of hybrid quantum classical systems. And, you know, ideas for kind of, okay, how do you kind of construct a generator for this hybrid system? Well, I would say kind of perhaps a natural use of this influence functional formalism is to kind of essentially generate some effective stochastic equations for instance, a quantum system with a classical environment, or vice versa, that we can kind of see actually precisely what the difference is between having a quantum environment and having a classical environment. I think kind of, as I have kind of, I think that's about everything I have to say here. Yeah, thank you for your attention.
Thank you so much. So there's plenty of time for questions.
May I ask the question?
Yeah, sure.
So when you are talking about this open quantum system, as I understand, it means that you have a quantum system and you have an environment, and the quantum system, which maybe you are trying to build some device or something else, is somehow interacting with the environment, and you have not much control over it, but you are trying to control over it, right? Okay. Now this environment that you assume is obviously classical. Am I correct?
In the case that I've been looking at here, everything is classical. But in the case of the original equation I showed you, it's a quantum environment. It's interacting with a quantum system. They both are evolved by the Hamiltonian rather than the Poisson bracket.
So your environment is quantum by nature.
Yes, in the original case. So and this is part of what is kind of a little bit difficult about taking the classical limit of that equation. That because the environment is also quantum, that's why the correlations in your noises kind of feature this factor of h bar. Whereas when you classicalize the entire system, you kind of see, I mean, if I go all the way back, right, that quantum system, quantum environment gives you, if I keep going, this kind of term, right, that both of your kind of correlations, which are representing the effect of the environment, have h bar in them. And while you can kind of take a classical limit for one of these noises, the other one, the fact h bar is in it, makes it seem to disappear. Whereas if I have a kind of classical environment, classical system, and I can perform the same procedure, those correlations become changed, right? The difference being that factor of h bar that was there for the quantum environment is completely gone now. So yeah, this there is a kind of so far, like, I don't think anyone has kind of repeated this procedure with either a classical environment and a quantum system, or a classical system or quantum environment, whatever that means. Does that answer your question? Okay,
I understand. Actually, what I was thinking is, when you have a quantum system somehow interacting with a classical environment, how do we know that classical environment doesn't dominate the whole thing? Like,
well, I mean, this would be a way of kind of understanding this, right? That you have a joint quantum classical Hamiltonian. You should be able to put that as a path integral and then be able to kind of integrate out the classical environment, which will give you an effective equation of motion for the quantum part. And there, you know, I think it should be kind of pretty, you know, you can kind of analyze what that tells you, you know, is the noise kind of completely dominating that evolution in that case?
Okay, we can discuss more maybe in the other sessions.
Okay, Professor Diaz.
Oh,
I think you're muted, Professor Diaz.
Yep. apparently your model resembles the so-called Caldera-Leggett model.
Yes.
And some long time ago, they calculated the quantum the radius dynamics of the system. They traced over the degrees of the freedom of the oscillatory bars. Mm-hmm. Does your result include the now standard Caldera-Leggett result or not?
Yes. So, I mean, the model there, I would say, kind of is almost exactly Caldera-Leggett. The difference being, I would say, going back to this, is that the Caldera-Leggett model kind of includes a counter term, right, to enforce translational invariance in it. Now you can include this counter term in this Hamiltonian.
Yeah.
The difference is that then the kind of the initial condition that you'd like to take, you actually want that your initial condition for this rho beta part should actually also include the interaction with the Q system as part of it. And then what happens then is that when you do the integrals, you see that extra term in the Hamiltonian and the extra term in the initial condition, as you're integrating, will cancel themselves entirely. So yeah, the result you get here is kind of completely equivalent to the Caldera-Leggett model. And so this should be the classical limit of that model.